Too serious. Yeah.
Market on Lord.
What was that?
You should market on Lord.
Is this going to be an internal wave 101?
Actually, it's going to be a tides 101.
False advertisement.
Yes. Well, we'll get to the internal waves. That's where we're heading towards.
Some of them have an interest on internal waves. In fact, they have on what we call dissipation systems, which are at about 30 to 150 meters. We know that they do have impacts.
That was the migration depth.
And also, because in some cases they make it this close to polar water. That's the way.
Right.
Morning. I think let's get started. Thank you for attending, and it's my great pleasure to welcome and introduce Dr. James Richman. Jim is a really interesting person. He got his undergraduate degree in physics from Harvey Mudd College in California, and then got his PhD in physical oceanography from MIT Woods Hole Oceanographic Institution. After that, he spent the next 30 years being a professor in physical oceanography at Oregon State University in Corvallis. And after that, he announced his first official retirement. For the next 8 years, he worked as a senior scientist and oceanographer at Stennis Space Center Naval Research Lab, where I had a great pleasure to work with him on many interesting projects for about 8 years. So last year, he announced his official second retirement from the Naval Research Lab, U.S. Navy. Right now, he's a part-time senior scientist at Florida State University working on global tide high-resolution modeling. And his real full-time job is raising 38 sheep, goats, and lambs in his Oregon farm in Corvallis, Oregon. So he's going to talk about the internal tide and internal waves for the global ocean models. I know we have many participants dial in remotely, so we appreciate you attending this webinar. If you have any questions, please type in, and Nicole here will be relay your questions, and Jim will answer after his talk. All right, thank you very much, and let's welcome Dr. Jim Richman.
So in the vein of truth in advertising, I will eventually get around to internal tides and waves, but you're going to have to bear with me on tides for a while rather than internal tides. What I'd like to talk about today is work that's being done at the Naval Research Laboratory in the Oceanography Division down in southern Mississippi. And this work's being done in collaboration with actually a bunch of people here. So Brian Arbick at the University of Michigan, and Martin Buseman, who's at the University of Southern Mississippi, and Jay Shriver, who's at NRL Stennis. We're all here for a project meeting with Brian. And so I've been involved in a lot of this, but in fact, most of the publications that I will pull pictures from and stuff like that are actually from the group in the back of the room. And so if you really want to ask questions, you can go corner them. But there's quite a number of people involved in getting this going. Sorry. Okay, so one of the major activities that's done in the Oceanography Division is developing a global ocean forecast system. So it's effectively a weather model, but for the ocean. And in this forecast system, there's two major parts. There actually is the dynamical model that makes the forecast, and then the data assimilation system, which is used to take observations, blend them with the model to give you an initial condition to run your forecast forward. And so right now, this is being done routinely by the operational Navy, and you can actually look at those routine things, products, either on the NRL website, or you can get the data itself from Florida State on their server for HICOM. But every day, you run forecasts out for 7 days. And the current system is based upon a 1/12 degree, that's about 8 kilometer resolution globally. That's what's considered an eddy or weather resolving model inside the ocean. And the plan is to transition this in a couple of years to a 4 kilometer resolution model. Just to give you a sense, 4 kilometers is basically about 10,000 points by 10,000 points in the horizontal, and then there's 41 layers in the vertical, and we generate about, bear with me, Jay, it's about 10 gigabytes of data for every snapshot that you create on this. So it generates a lot of data very quickly to look at what's going on. And in this model, one of the biggest things we'll do is also add tides. And just up here on the screen, you'll see an animation which is, I grabbed a while ago, and this is the sea surface height, the predictions from the model, and as I said, every day you do an analysis and you run a forecast, and what you're looking at right now actually are the analyses. That is a snapshot of the model once a day, and this is done for a year. And these forecasts are then used by the Navy for decision aids, so things that we don't normally think about, when they want to go launch and exercise or whatever. They're used to predict the acoustic properties in the ocean for finding submarines and things like that. And they're also used as provide boundary conditions for regional models. And in those regional models, traditionally what you do is you take the large-scale model, ocean models, boundary conditions, and you add to it a barotropic tide. And then you have the tides in near the coast where you want, and you then have a new set of decision tools and forecasts that you can make. But there's been recently a fair amount of information that's come forward that says that indeed tidal information propagating from far away into the regions may actually affect the regional solutions. And so the decision was made to sort of say, could we in fact put tides directly into the global model and make a forecast of the tides as well as the ocean circulation? And Brian did that in this model. And so now we actually have in principle a model where eventually we'll be able to predict not only the ocean circulation but the tides. And it turns out that when we put the surface tides in, the traditional one you see that makes everything but lakes go up and down, when you put that into the ocean, as those tides move over bathymetry in a stratified ocean, they generate internal waves. And to give the punch line away a little bit, that in turn actually is generating a very robust internal gravity wave field, not just at tidal frequencies, but across the entire range of internal wave frequencies in this model. So it's been a very exciting evolution that we've had over the past few years. Well, I thought I had the things. So on the screen, there should have been little boxes about the things that were added to make you go from a standard sort of shallow water model to a tide model. So if you look up there, you'll see that traditionally there's the normal equation of motions. You have the pressure forcing, and you add two new terms. One is the gravitational equilibrium pressure forcing, if you want, from the attraction of the sun and the moon, which is called eddy equilibrium. And then you actually have to provide a correction, which is called the self-attraction and loading, which is in fact the Earth itself deforms. You have solid Earth tides. And the water, as you move it around, you're moving around a fair amount of mass, and that mass actually attracts itself, so it has a self-attraction. And then you have bottom friction as a quadratic drag. It's the next term over. And a new term, which is in the barotropic tide model, represents the generation, the conversion of the tidal motion itself into internal motion. So it's represents now a loss of energy, an internal wave drag. And then finally you have the other forcings you have. Internal friction, wind forcing, features like that. So NRL uses what's called a tripole grid. It just happens to be the way. And we've added the attractions, the equilibrium tide, that is to say the gravitational attraction of the sun and the moon, and we've added then a self-attraction and loading, the correction for the actual movement. And initially this was done in a very simple way, just making what's called a scalar approximation, a very crude way of looking at it. And you solve this solution, and then you get a better solution by then either tuning it, varying the wave drag or bottom drag coefficients, and then you also can go back and iterate, as it's called, or you can say, well, this scalar approximation isn't really a very good approximation, but I have to know what the height field looks like to actually figure out what the self-attraction and loading is. So I solve it, I take this field, I get a guess for what that is, I put that back in and solve it again. And there are two parameters that you can tune in this model if you want, one of which is the bottom drag, the quadratic bottom drag, the CD, and the other is this linear internal wave drag, which is called C. When I started out as a graduate student in the dark ages, nobody actually thought about the internal wave drag, it was all the drag in the shallow water. That's where the quadratic drag applies because that's where the velocities are much stronger. And so, people were trying to tune the drag coefficients on the Patagonian shelf and other places. It wasn't really until the advent of satellite altimetry. Do everybody here know how a satellite altimeter works in principle? Right. So you've got a radar up in space, and the typical ones we have, they're 1,000 kilometers up in space. They send a pulse of microwave energy down to the sea surface. It reflects off the sea surface, and you measure the travel time between the satellite and the ground below it, in the ocean in this case. And then you actually spend a lot of effort to track out and find out where that satellite is relative to the surface of the Earth. And you have to make corrections for the fact that microwaves, actually the speed of light changes as you go through the medium, so there's actually a change in the travel speed. You go through all this and you can actually make this measurement of height of the ocean. Now that comes back rather infrequently, every 10 days or thereabout, but because the tides have a well-known period, I can actually recover the tidal amplitudes out of this signal. So suddenly I had the ability to look at the tidal amplitudes over the entire globe instead of just at isolated points along the coastlines or islands. And then when that information was sort of blended back with this sort of simple dynamical model, realized that in fact something like 40% of the energy in the tide is actually dissipated in the open ocean. And so it led to this including of internal wave drag into the models. But we can vary these things to try to improve the accuracy of the tide. And that's where my boxes went, sorry. Okay, so just as a thing, so I can tune these things, and then I look at the difference between some truth. And that could be tide gauges, it could be bottom pressure gauges, which are deep water tide gauges, or it could in fact be one of these altimetric representations of the tides. And then I'm going to adjust my parameters and fiddle with my model a little bit to try to minimize the RMS difference between what I think the real tide is and what my tide forecast is. And something that Martin did very nicely is show that if you look at where you actually have the minimum RMS, the smallest difference, that would be the best comparison of your height signal to the other signal, isn't necessarily at the point that might have the dissipation that I need to balance out. One of the things I really know about the global system is the sun and the moon and the Earth system dissipates energy. That's known very well, and so astronomically that's a constraint on the system. And so I need to have that much dissipation in my model. And so there's some additional physical understanding that's needed to kind of get a really good description of the entire internal and external tidal systems. So one question is, how well do I actually know the tides? So this is a very busy slide, but just bear with me. There's a recent paper with a lot of people trying to compare the best tide models with 151 deep water gauges and then a whole series of continental shelf and coastal tide gauges. Actually, they looked in the Arctic and the Antarctic as well. And so there are 7 models that were sort of in this competition. The 7 models actually agreed pretty well in general. And when you compare them to these deep water tide gauges, which were not used by any of the models to actually create their solution, then it turns out the RMS error globally in this main semidiurnal tide is 0.5 centimeter. Okay, so it's pretty small. So that's the target that we would eventually love to be forecasting. When we started all this stuff, the target was about 2 centimeters. So the tide modelers are getting better with time. But so this is how well we actually think we know what's going on. But there's differences between those models and how they work, and we need to figure out the sort of solution we have. So that given, then we took that additional forcing and we put it in the three-dimensional model, and then we came back and we can look at the tidal solution. So with all those simplifications that I talked about initially, we created a tidal simulation, and the RMS error that we had in this first look was 7 centimeters. It's quite a bit bigger, but it's still not too bad. And if you look by eye, the sort of best barotropic tide model, this is from the TPXO Egbert et al., and our tidal solution qualitatively and quantitatively look quite close. It's just there are much larger differences in these models than when you actually look carefully relative to the things. And if you actually look at the error, so this is now the difference, the RMS differences between those two pictures that I had, you can see that in this first solution we have very large errors all around Antarctica, very large errors in the Atlantic, and we have some significant errors in the Pacific and Indian Ocean. And you can think about characterizing these errors. Are they errors in the absolute height, or are they errors in the timing, the arrival of the tide itself? And so particularly in the Pacific, come back, those big blobs in the Pacific tend to be more errors in the timing of the tide rather than errors in the height of the tide. But overall, it's about evenly split. So my error budget says about half that error is associated with having an incorrect amplitude, and about half that error is sort of associated with an amplitude-weighted phase difference. So it turns out that in the course of doing this, we also noticed that the tide modelers themselves did some things to extend the ocean underneath the ice shelves, which we hadn't done in the global circulation model. And this model had a scalar SAL, sorry. So we came back and thought about what things we could do to it. But the other thing to bear in mind is, as we begin to really evaluate this, is that we do know something about how much energy is dissipated astronomically. It's about 3.7 terawatts. And the principal semidiurnal tide dissipates about 2.5 terawatts, and most of that is in the ocean tide. And then there's this range of uncertainty that comes about, which is how much of that is in the shallow seas and how much of that is in the deep ocean. Because shallow seas, I might be able to change that by changing the quadratic drag coefficient. Deep water is going to be changed by changing the amount that's converted into internal gravity waves, internal tides. And as you can see, approximately sort of on the order of about 40% of the energy is being dissipated in deep water. So that's kind of a target that we need to have as a sanity check for any model that we are producing. And Martin actually, in a paper, looked at the tidal dissipation that comes out of one of these barotropic tide models and the corresponding tidal dissipation that comes out of our model. And I think you can see that qualitatively they're very similar. There are differences somewhat in the magnitude, and we tend to have very much more narrowly focused regions of higher dissipation compared to the barotropic models. But again, we're passing the sanity check, if you want, and we're in the right quantitative ballpark for the solutions that we're getting. Okay, so the answer is that we created the solution. It's pretty good. If I take my glasses off, and I'm very farsighted, so things look nice and blurry. they look very, very similar, you know. But I put my glasses on, and they don't really work as well as you might like. So what are the things that we can do to improve the model to try to get a better tide? So one of them was the self-attraction and loading. The problem is that the way that the self-attraction and loading is traditionally done, this iteration, it works very well in these barotropic tide models, which can be linearized and done in a frequency domain, so you only have to do this iteration every so often. But I'm doing this model is a global forecast model, and so I have to run it for a long time to try to extract the tide, to try to do the correction, and much of the elevation variations, the mass changes I might have, are not in fact associated with the tide, but associated with the wind-driven and ocean circulation. So the iteration, it's possible to do, but it's not something that we'd want to do routinely. But when you're trying to see what it takes to get something right, you can afford to do these sorts of things on a limited base. So we know that we can improve things by improving the representation of the self-attraction and loading. We also basically changed out the form of the wave drag, which just makes it a little bit easier for us to do some tuning experiments. And we extended the domain of the model to include the ocean underneath the floating ice shelves. And so we then generated a new solution, and this new tidal solution went from 7 centimeters to about 4.4 centimeters. So it's a significant improvement. It's still a ways away from where we'd like to be in that. So, so the best barotropic tidal models do data assimilation, but the technique that they use for data assimilation is not possible to be used directly in the forecast model that we have. So we borrowed an approach from data assimilation to try to come up with a way to get a better tidal forcing for our model. And this actually was a pretty innovative piece of work which just recently published on a paper by Hans Negodak and all of us. And so the technique that we're going to use is formally called an augmented state ensemble Kalman filter. I'll go through a little bit of mathematics, but just listen to the words and don't worry so much about the equations. So what I have is that over time, the sea surface height and the velocities are going to change associated with the forcings that are applied to them. So this gravitational attraction, what have you. And in a perfect model, that would just be this sort of dxdt, the change in height and velocity is equal to all the forcings applied to the thing. So it's just F equals ma if you're in physics. And then, but I do this as a numerical implementation. I don't know everything perfectly. So I have some error in my forcing, okay? Some error in the forces being applied. That's this little f, okay? And then I have some observations, and we'll call those capital Y. And those observations are relatable back to the things that I actually try to predict. So sometimes you might not have an observation which is actually something you formally predict. So for example, the biologists here use ocean color, right? And the observation is ocean color, but you may predict chlorophyll, okay? So you have to have some, some way of changing the color to chlorophyll, okay? So this fancy little H is nothing more than a matrix which takes that. Now, I'm only going to look at sea surface height, so actually my H is 1, so it's pretty easy, but it doesn't necessarily have to be that. And then there's some error. That is to say, the observations themselves are not perfect, okay? So, and I'm going to then blend those two. It's in the parlance of data assimilation, I'm going to create an analysis, the blend of the model and the observations, and I'm going to do that by having some statistical description between how the observations are related across themselves. And I'm probably butchering this for the real data simulators, but it'll work for the moment. And in this particular case, I'm going to generate this statistical correlation by creating a whole bunch of different representations. That is to say, I'm going to take the model, I'm going to kick it away from reality a little bit, and I'm going to run the model. It's a nonlinear model, and it's going to generate me a slightly different solution. And I'm going to take all those kicked estimates, blend them together to build sort of a statistical relationship. So that's my ensemble. Let's go on. The little f, the big F, that's all the forces. So that's the small f is the error in the forces. It's the things I don't know about that. So it could be, for example, I get winds from someplace, but they could be wrong. I have a numerical implementation. So, for example, in the tides, I don't necessarily represent the bathymetry of the coastlines accurately. I have numerical error that comes in. So it's all the things that cause me to have an error in actually predicting the evolution given the forcing that I have. So if you want to think about it, just like the observations have error, the model itself has error. So I'm just going to represent that by some forcing term. And this one gets a little bit small, but effectively I'm going to augment the state vector in this case. So I have the height and the velocities that I estimate. And now I'm going to say, well, I also can make a prediction of that error, that little f that I have. So I'm going to add a stochastic equation for that little f. And now I'm going to make a prediction using my machinery of data assimilation of not just the actual state of the tides, but the best forcing that I would apply to the tide model to give me back that best state. Okay. So this is the augmentation. And remember I told you that I'm going to take the model and I'm going to perturb it in some way. So we had that pressure forcing term, which was G, grad, eta, plus eta equilibrium, plus eta SAL. And I'm going to put an additional eta perturbation into that. And this is kind of one of the perturbations that I have. So it's a little bit blurry for the room, but the darkest colors are 8 centimeters. The average height of the M2 tide over the ocean is about 30 centimeters over deep water. So I'm putting on a perturbation just roughly on the order of about a third of the amplitude of tide. And we generated this randomly, and the scales of this kind of looked like what that self-attraction and loading field looked like, just how we did it. So we created 100 of these perturbations. We ran the full 3D model with this extra term 100 times for a month to get this new set of ensemble members. And then I actually can't run the ensemble Kalman filter on the full 3D model because you didn't see it in there, but I have to invert a matrix. And so if I did it on the full 3D model, that would be 41 by 1,000 by 1,000 by 5 inversion. So that requires calculations which are that big raised to the third power. I can't do that. So we made an assumption, which is to say that we think that the tide solution, in some sense, isn't strong in modifying the global ocean circulation in a fundamental way. So I can analyze the tidal solution from each one of those 100 ensemble members, and instead of doing the estimation of the full ocean state, I'll just do it for the tidal height, which is all that I actually have data. So I come up with a new sort of state estimation, which is just really the estimation of the sea surface height, the tidal estimates of the sea surface height, and I'm going to come up with a new forcing function, which is just that piece that I would add to force one. And I'll do that for each of the tidal constituents that I have in my model. In this particular case, we had 5 of them. So then you can run this machinery and you come back with, this is that little f, that forcing correction. So this is the height forcing that I would apply to the model. to give me the best tidal solution that I could have. And you can see that it's very, very large in the Atlantic Ocean, but there are patches around the globe to fix the solution. Sorry, I'm not sure why I keep bumping it the wrong way. Okay, so we did a number of different experiments looking at that, and primarily we varied how tightly we wanted to believe the observations. And so you remember we started out with a global RMS of 7, and we actually also looked at it, which is to say that there's a distribution to the size of the errors. We said we can look at the average over the whole globe. We can also find what's the middle value. So half the errors are larger than that, half the errors are smaller than that. That's the median. And we can look at it in terms of the Atlantic and the rest of the globe, excluding the Atlantic. And I'll come back to that because the Atlantic is our biggest problem. And so I started at 7. Then we did the one where we changed the geometry, we changed the drag and tuned the drag up a little bit, and we extended the domain to include the energy. So we got to 4. And then you can see a whole series of solutions where we're down at between 2.5 and 3 centimeters. There's one in here that technically is very interesting, which is we made a slight mistake. We said, believe the observations that they just actually have to be really, really right. So we said the obs error is only 0.5 millimeter. Okay, and you can see that solution is not significantly different than the rest of the solutions. So this was one of the questions we had to address. This is the corresponding map of amplitude and phase for this extended Kalman filter that we had, and that's actually the data set that we were assimilating. That's the TPXO data set. And so again, by eye, you know, they look very, very close. And so the RMS error for those two is only 2.5 centimeters. Okay, and if I go and look at those differences, so this is the difference point by point of how big is the best barotropic model from the observed, from the solution we have, and of course, so this solid line is the median solution, median error. And you can see as I go from the initial solution to my sort of best iterated solution to 2 of the solutions that I looked at from this augmented Ensemble Kalman filter, that globally you can see that I basically am collapsing the error. I'm moving it farther and farther to the left. But you can still see that I have some tails out there that are really, really large. But if you look at the Atlantic, you can see that actually the Atlantic is kind of behaving not nearly as well in this case. And so that's where the errors in this particular model are really dominating. Okay, and if I just come back and sort of show you a picture. This is a picture on the same color bar of the error between, the RMS error between the best barotropic tidal model assimilating data and our solutions. And so that's our initial solution up on the top left, the solution that we sort of did when we changed the geometry in the SAL. And these are a couple of the solutions from this augmented state Kalman filter. And so I've got the error down to this sort of 2.6 centimeters, which is good. We'd like to do better. And we particularly would like to do better in the Atlantic. And then the other thing is I told you that what we did was we also predicted that correction. So, so I can come back and say now I can rerun the 3-dimensional model with that new forcing correction. And of course the background ocean underneath it won't be exactly the same. And the tidal solution isn't going to be exactly the same. So the differences between these two are the differences between the prediction of the Kalman filter and the prediction of the model. And again, you can see that the way it's set up, if you see a blue color, that's actually where the the force model actually is doing better than the prediction, and the warmer colors are where the prediction was actually better than the force model. But these errors are really quite small. I mean, the color bar I'm showing you on here is plus or minus 5 centimeters. Okay, so just in the sense of getting to the point that this is the starting point of where we'd like to be, there's one thing. Why didn't I get a better Atlantic solution out of this, even when I told it believed the observations? Well, there's a subtle point in an ensemble. When you do this ensemble Kalman filter, the correction is basically a combination of the members that you had in the ensemble. And so if the ensemble never generates an improvement in a region, you can never make any correction to make it better. So that's what we think happened in this particular case, that the large-scale forcing perturbations that we applied just didn't make a big difference in the Atlantic. I mean, they made some, but not as much as we would like. Okay, so so we're proceeding with two approaches to try to look at this. One of which is to look at putting nested domains in the areas where we have big errors to try to get locally a better solution. And the other is to look at it and generate a new set of perturbations which have smaller scales to represent the character of the errors that we've got. But that given, we can actually go ahead and use this model to look at what's happening in the ocean when I have the tides in concert with the global circulation. So when the tide flows over topography in a stratified medium, it generates an internal wave. That wave happens to actually be at tidal frequency, so we call it an internal tide. It's an internal gravity wave. And so these are the internal tides that are generated inside the three-dimensional model that we had, where we're now. And one of the things you'll notice is that there's very strong generation in patches, and those tidal energy propagate away in beams that actually travel for quite long distances. Okay. And so it was exciting to see this in the ocean model. Of course, the satellite people had actually seen it beforehand. And then the other is that why don't these beams go all the way to the other coast? What's happening to them? Why do they appear to dissipate when you propagate them? And it's an important question because it turns out it could be that all that's happening is that the beams are being scattered, but that means that they develop a random character to them, and so when I do a harmonic analysis, they appear to disappear. It's what's called, they become incoherent. Or they could actually be being dissipated, that is to say the energy is being lost. What's going on. And just to sort of follow up with what I said earlier, on the top is what the altimeter actually saw for the surface signature of internal waves. If you look at the color bar here, it's 1 centimeter plus or minus. It's 1 centimeter total. So remember I have that satellite, it's 1,000 kilometers out in space, and I'm actually now looking at signals that are this big, 1 centimeter in height. It's remarkable how far we've come with that thing. But if you look at this thing, the pictures here, we analyzed the model heights exactly the way you recover this thing from the altimeter. The altimeter tracks are about 3 degrees apart. So there's all these white spots. That's just, the altimeter never sees it. So it's not that there's no tide there or anything. It's just that we don't see it with the altimeter. Okay. That's just the orbital mechanics. You can't make a satellite behave completely independently like you'd like. But if you again, you see that the satellite sees those same sort of hot spots that we saw in the model, and you can see that It's not as easy, but you can see that those beams don't go all the way to the coast. They appear to dissipate. So when we actually look at that, and we can do things in the model that you can't do with the altimeter. So one of the things we find is that as you look at the tide, so I can run this for the model for a long time, and then I can do harmonic analysis to pull out the tide on short bits, and I can say how much, from month to month, how much does the semidiurnal internal tide amplitude vary. And I can get a measure of that standard deviation. So if it varies a lot, that means it's not a particularly coherent signal. If it varies very little, it's a very coherent signal. So if you look on this picture, you see these bright spots of quite incoherent, large standard deviation with these blue spots in the middle. Of course, that's where the generation is. So very close to where the tide is generated, it's very coherent. And as I propagate away from that, it becomes less and less coherent, it becomes incoherent. It hasn't necessarily dissipated, it's just that the technique that I'm using is not able to describe it in a consistent fashion. And there's an experiment that was done by Ponte and Klein. They did an idealized experiment, and so they have this little channel, and in the channel they have basically an unstable jet that's going across, it's generating lots of eddies, and they put a wave maker in here that generates an internal tide and it propagates across. And so if you look at it, which I guess I'm supposed to point it, sorry. If you look at the signal, you can see that in the near the wave maker, you've got these nice plane fronts that come across. They hit the eddies, and all of a sudden it becomes this very chaotic sort of thing. If you look at the far right panel, that's a measure of the energy. So it's kind of the amplitudes of these things. And so you can see near the wave maker, everything is fairly coherent. Okay, so, and I hit that cross channel, and I go from being a very coherent signal, the dark black, to being a very incoherent signal, which is the lighter color. But in this particular case, if you notice, there's a slight decrease in the amplitude, but it's mostly that I scattered it rather than I dissipated it. So this is kind of a interesting result, which has consequences for where is the tidal energy being lost into the system. So these are some new things that we've discovered with the tides. It also leads to the fact that there might be some hope that we may be able to predict some of the internal tidal energy. Usually you talk to people and they say that along the coasts everything's incoherent. But if in fact I have strong beams that are generated, and I actually knew all the refractors between where I generated it and where I am, I might actually be able to make some statement about what actually is that, what we would think of incoherent part of the beam. So we're trying to look at ways to see whether or not you can actually verify that in the model and how you might actually look at that in reality. And that would help us a lot, because now it would say, remember I said that initially we thought the internal tides coming from far away might change the regional solution. They might affect what you're doing. Well, but if they're incoherent, if I have no knowledge with them, I don't know how to put them into a boundary condition in some way. But if I can tell you something about what is apparently incoherent, that is, it's not simply related back to the original source, but I was able to trace it along through all the scatterers, I might be able to make a better prediction of what's going on. And then lastly, I'm going to fill in, remember, an internal tide is just an internal wave at tidal frequency. Well, in the mid-70s, Chris Garrett and Walter Munk came up with a prediction of the statistical shape of the frequency spectrum for internal waves. Okay, it's called the Garrett-Munk spectrum. And so they found that within a few slight tunable parameters about this, what the stratification is, and a little bit about how the structure of the thermocline functions, you can make a prediction for what the amplitude and shape in frequency for the internal gravity wave field in this case. So the black line is this Garrett-Munk spectrum. The red line actually is a mooring, an observations from a mooring. So this is the just a current meter that's out there for a long time, and we just did the spectrum of that. And the green and blue lines are two of our simulations from the global model with the times. And so the blue actually is the 8-kilometer model. That's the current forecast system that we have. And the green model is the 4-kilometer one, the much higher resolution model. And I think you can see that in fact, with this increasing resolution, you're seeing more and more internal wave energy appearing, and we're beginning to get the model to approach the observations in its character. And I didn't pull it off, but there's actually now a 1/48th degree global model that's been run by people using a different model at the Jet Propulsion Laboratory. And if you make this plot, it does even better. So as the resolution of the model is increasing, we apparently are, in fact, generating internal gravity waves now that we've added the tide. So the question is, you know, how am I really actually doing this, and are these really internal waves in the proper way? So one of the things about an internal gravity wave is it has what's called a dispersion relationship. That is to say, the horizontal wavelength of the waves and the vertical wave number, or the vertical wavelength, and the frequency are all related by something that's called a dispersion relationship. So if I have a frequency and I have the horizontal wave number, then I also know what the vertical wave number is. Now we can do this in terms of what's called vertical modes. It's just a different way of describing it. So on this particular plot, the color is the frequency wave number spectrum from the model for the internal gravity waves. And the white lines represent the range of the dispersion curves over this box. The box was rather big. It's about 10 degrees. And over 10 degrees, the Coriolis frequency and the stratification change a little bit. So there's some blurring of the dispersion relation. It's not a simple line because you've changed the environment. And you can see that what I've got is the energy that I was filling in the model that you saw in the frequency spectrum is actually also filling in on the model along the dispersion curves. So the brighter colors fall on those lines. And I've highlighted what's modes 1 to 4. Actually, by the time you get to 5, 6, and 7 in the model 1, we don't generate those very well with the resolution we have in the vertical. And the other is they begin to collapse enough that they all lie on top of each other. So this other big band that you see is really kind of where all the high modes are sort of collapsing on each other. So this is confirming that, in fact, that energy I see is actually looking like internal gravity waves. So I really am generating internal gravity waves inside the global model. And then if you look more carefully, this is a calculation that Brian's brought to the table. We can actually do and look at, so where are the nonlinear transfers? That is to say, where am I taking energy from one wavelength and putting it into another wavelength? Okay, so this is a picture of the places I'm extracting energy from and where I'm putting energy into it. So you'll see that circled, those little bands of blue, those are the internal tides, very narrow speaks, so it's the two primary sets of tides. And then you see down here I also have a band that's associated with the near inertial, that's the wind-driven internal waves. And I'm taking energy from those waves. So I added internal tides because I put the tide in. I gave it a source of energy that I'm now extracting from, and the color doesn't match really great, but you can see that I have red predominantly that's appearing into the places where I'm filling in that spectrum of internal gravity waves. And this particular approach would argue that it's what's called a triad interaction. So that basically means I have an internal tide wave, another wave, and those two things interact to generate a third wave, and that's how I move the energy around. And it also helps explain if I went back a few pictures to that frequency spectrum that I showed. You remember the blue line seems to have these big bumps, and that's because I'm beginning to get a very discrete sets of waves that I can do, so the triad interaction can't fill things out smoothly because I don't have the resolution to actually fill in the wave spectrum. So now we actually have, in a global model, we have a prediction of the barotropic tide, a prediction, if you want, of the ocean circulation simultaneously. That barotropic tide is generating internal tides, and the interactions with the internal tides and other motions are in fact generating internal gravity waves. And so I have an increasingly realistic picture of what the global ocean looks like. And we know, for example, that we think if we increase the resolution of the model, we should do a better job in filling in the internal gravity wave spectrum. It's just that's a very expensive calculation to do. And so I've summarized a lot of other people's work and probably not given it adequate justification, but I think you can get a sense for what we, or at least I feel, is a really exciting modeling and enhancement and advance that we've made. And we're kind of proud that people have picked up on that and realized that it can be done. And so there are other groups around the world that are trying to add this into their global ocean models. So at that point, I'll take any questions that people might have. Yes?
One is the drag coefficient and the C for the different times. What the magnitude?
Okay, so the question that was asked in the room was basically what are the size of the drag coefficient and the for the quadratic bottom drag and the drag coefficient for the internal wave drag. So the bottom drag is 0.0025. It's just kind of a typical number for CD. Huh? Yeah. Okay. And the C, the actual value of the C is kind of not independent with the choice of the roughness field. So we use something that's called a Jane and Saint Laurent. So it's a variable drag field, and we also had to do something which is that we have to clip it because the actual roughness can be too large, which makes the numerics unstable in places. And bear with me. Do you guys remember what the full drag numbers are? I'm so used. Okay. So it's about 2 times 10 to the minus 5 days to the seconds to the minus 1.
And second question is the Atlantic Ocean at largest level.
Yes.
And compared to Pacific.
Right.
Pacific no boundary, so like atmosphere. And Atlantic is the ocean feature of a 2 boundary, very narrow. And I wonder the common filter not dynamic system is ocean dynamics, because you just do the collection but not consider their internal dynamic equation. So I mean, even trying and sampling, I guess it's as you told you about with like the Gauss integration of the dynamic model is needed to reduce the substantially increased energy?
I'll try to, for the remote audience, I'll try to summarize the question a little bit. So the question actually comes about from the data assimilation, which is to say that the solution was better in the Pacific than in the Atlantic. The Pacific is kind of a very large ocean. The Atlantic is much smaller, so geometry and may actually matter, and the Kalman filter doesn't know anything about dynamics. It's just a blender, and so it may in fact not be the best way of trying to blend with the data. The suggestion is potentially something like a 4D VAR, which would give you a measure of the dynamics into your data assimilation. It's probably the case. The difficulty is trying to sort out how I do 4D VAR on something which has really quite different physics. The physics of the tides, particularly the internal tides, for example, are very different than the physics for mesoscale eddies. Yet a mode 1 internal tide has the same general scale as a mesoscale eddy. So we haven't quite figured out how to do that. But maybe a different answer to your question is the tides have resonances. Okay, so there are certain areas, the Bay of Fundy, Hudson Strait, the Bay of Biscay, actually Sea of Okhotsk, some of these, where you have very, very large tides because you actually get resonances in what's going on. And work that Brian has done with Chris Garrett actually show that those resonances that are local actually affect the global tidal solution. So that's why we've been thinking that if we could get perturbations or we could nest the models to get the models to be capable of resolving those resonances, that we could improve the tidal solution. So that's the approach that we're taking rather than trying to pursue a 4D VAR data simulation. Nagodok et al. In Ocean Modeling 2016. But if they want to email me, so you can get me at james.richman.ctr@nrlssc.navy.mil. Or if that's too long, you can send it to my farm. It's jr@cornercreekfarm, all one word, .com. And I'll get back to you with a full reference and a PDF of the paper. And then there's a question you had, yes?
Yeah, I guess I'm trying to understand exactly what the beams are. They originate from a topographic feature and go in the direction of wave propagation.
So what actually happens is if you sort of think about it, you're propagating over and you're hitting a sort of a facet, if you want, a bit of topography, and so you generate a wave. And so it's that's where the wave maker is. Okay, so in the reality, I've got all these wave makers, and so they themselves kind of create these planar waves that come out from the facets. So if you look at it, sort of, you can identify kind of the major generating topographic features. They each have a beam associated with them. So if we walk back.
I'm just kind of wondering to what extent they diffract sideways.
Well, okay, so the fact of the matter is they're not, it's not like a point source which would give you a radial beam. They're really from a sort of a flat facet. So it tends to give you kind of a plane wave type generation of limited scope. And so yes, that beam will disperse over time. So part of the loss that you see here could in fact be the beams dispersing. Although when you look at this picture, it's not like that's the dominant color feature that you see, which is the beam just kind of disappearing because it's going up. But, I mean, they seem to be keeping their structure relatively coherently for a fairly long distance. So I don't know if that answers your question, and I forgot to repeat the question. The question actually was, why do I see the internal tides being generated in these very narrow beams? What's the actual mechanism for generating them, and why are they in these tight beams? And at least my sort of intuition is that it actually just has to do with the character of the way that you generate the waves by interaction with a critical slope, effectively. And if I'm really off base, chime in, anybody. Any other questions? All right, thanks for bearing with me, and I hope at least it was interesting.